In this example, one of the six trigonometric ratios has been given to us and we are asked to find out the remaining five. Let's first draw a right triangle ABC. Now we know that tan of A is equal to BC upon AB, which is equal to 4 upon 3 as given. Therefore, if BC is equal to 4K, then AB will be 3K, where K is a positive number. Now, using Pythagoras theorem, we get AC square is equal to AB square plus BC square. Taking square roots, we get AC is equal to 5K. Now, as we know all the three sides of the triangle in terms of K, we can write all the trigonometric ratios using their definitions. Hence, sin A is equal to BC upon AC, which is equal to 4K upon 5K, which is ultimately 4 upon 5. Similarly, cos A works out to 3 upon 5. Also, cot A is the reciprocal of tan A, hence it will be 3 upon 4. Similarly, cosec A is the reciprocal of sin A, which will be equal to 5 upon 4. And sec A is the reciprocal of cos A, and it will be 5 upon 3. In the second example, the sine ratio of two angles belonging to two different triangles are given equal. We have to prove the two angles are congruent. So let us consider two right triangles ABC and PQR where sin B is equal to sin Q. Now sin B is equal to AC upon AB and sin Q is equal to PR upon PQ. As it is given that the sine ratios are equal, it implies AC upon AB is equal to PR upon PQ. Now applying alternando, that is exchanging the places of AB and PR, we get AC upon PR is equal to AB upon PQ is equal to K. We will call it as equation 1. Now if AC upon PR is equal to K, it implies AC is equal to K times PR, and if the second ratio AB upon PQ is equal to K, it implies AB is equal to K times PQ. Now using Pythagoras theorem, we get BC is equal to root of AB square minus AC square and QR is equal to root of PQ square minus PR square. So if we take the ratio BC upon QR and apply the values from equation 1, we get the ratio is equal to K. Therefore, from 1 and 2, we get that all the three ratios are equal to K, or in other words, the ratios of the corresponding sides of the two triangles are equal. Hence, by using theorem 6.4, we can say that triangle ACB is similar to triangle PRQ, and therefore angle B is equal to angle Q because of CAST. In example 3, the measures of two sides and an angle of a right angle triangle are given, and we are asked to determine the value of the combination of the trigonometric ratios of this angle. If we know two sides of a right triangle, the third side can be worked out using Pythagoras theorem. Accordingly, AC has been worked out as the root of AB square minus BC square, which finally works out to 20. Now, according to the definition of sine theta, which is opposite side upon hypotenuse, which works out to 20 upon 29, and according to the definition of cos theta, which is adjacent side upon hypotenuse, which is equal to 21 upon 29. Substituting the values of cos theta and sin theta in the given combination cos square theta plus sin square theta and further solving it, we get the value equal to 1. And also, if we substitute the values in the second combination, which is cos square theta minus sin square theta, and further solving it, we get the value 41 upon 841. In example 4, the value of tan ratio of an angle of a right angle triangle is given as 1, and we are asked to verify the relationship that twice the product of sine ratio and cos ratio of the said angle is equal to 1. If a ratio is equal to 1, it implies that the numerator is equal to the denominator. So, if tan ratio is equal to 1, it implies BC is equal to AB. Let us assume AB is equal to BC is equal to K, where K is a positive number. Now, applying Pythagoras, we can find the hypotenuse AC, which works out to K root 2. According to the definition of sin A, which is opposite side upon hypotenuse, BC upon AC works out to K upon K root 2, which is equal to 1 upon root 2. Similarly, cos A, which is equal to adjacent side upon hypotenuse, where AB upon AC works out to 1 upon root 2. Substituting the values of sin A and cos A as 1 upon root 2 in the given condition, we get the value of twice sin A into cos A equal to 1. In the fifth example, in right angle triangle OPQ, which is right angled at P, OP is equal to 7 centimeter and OQ minus PQ is equal to 1 centimeter, which implies that OQ is equal to 1 plus PQ. We have to find out values of sin Q and cos Q. Now applying Pythagoras theorem, we get OQ square is equal to OP square plus PQ square, and substituting the value of 1 plus PQ in place of OQ, we get 1 plus PQ square plus 2PQ is equal to OP square plus PQ square. Striking out PQ square from both the sides, we get 1 plus twice PQ is equal to 7 square, which is equal to 49. Therefore, twice PQ will be equal to 48, and hence PQ will be equal to 24 and OQ is equal to 25. Substituting the values, we get sin Q is equal to 7 upon 25 and cos Q is equal to 24 upon 25.